Okay, so there's not much to write down on this first page, but it's just sort of a reminder of some of the things that we've looked at. If you want to underline or highlight a few things here. The three top models that you're going to be asked to look at in any type of data modeling is linear, quadratic, or exponential. So in linear, we use a linear model when the data reveals a constant, a constant rate of change. Oh, it doesn't let me write things in here. Great. So we're looking for like a constant amount or close to it being added, right? Quadratic is when our rates of change are increasing or decreasing at a relatively constant rate. Remember with the tables, we did that second difference, right? We said, oh, how much is the original table going up by? That was not constant. But then we did that second difference, and those numbers were constant. Now, when we're modeling, they may not be perfectly constant. We might not get, for that second difference, we might not get 2, 2, 2, 2, 2, 2. On that second difference, we might get 1.9, 2.1, 2, 2.05, but they're pretty close in that case. And it's generally going to follow a U-shaped pattern or an upside down U. However, you can use like pieces of quadratics where you don't see like the minimum part of it there. And then exponentials are going to be used when output values are roughly proportional. So each successive output is approximately the result of repeated multiplication. There is a number you can multiply by to get the next number in the table, right? And we've looked at finding that pattern quite a few times. We will not see a linear rate of change. We also don't see a linear second difference either. We just start to see the same pattern repeat over and over. One of the big things that we are going to use to talk about whether or not a function is good are residuals. We talked about residuals a little bit already. We had a problem, I think it was talking about like the weights of the babies, and we talked about like how far off the actual is versus the predicted there. So whenever we create a model, remember a model is that equation, that is used to predict values for the dependent variable. So if we are going to look at residuals, residuals are the actual output minus the predicted output. So the actual is what comes from your table or like your actual data points, right? Predicted is what the line or the model says should happen for that. And residuals are going to be very helpful because residuals tell us how far off we are, right? How far off we are. So here is an example that we're going to look at with some residuals. An NCDOT salt shed used for storing road salt for winter storms holds 7,000 tons of salt. Before a winter storm began, the shed was full. The table to the left gives the amount of salt in the salt shed T days after the workers start salting the roads in preparation for the winter storm. A just says use the regression capabilities of your calculator to find a linear model of the form y equals a plus bx. Actually, I'm gonna change this right here. This would be better. Here's I put t's and s of t's and I didn't change this. S of t equals a plus bt. Let's use different variables right there. For that, ooh, I really shouldn't save that though because I highlighted this stuff over here and wrote those things. Hold on. see if I need to fix the damage I've done. Let's save that. And then I'm going to fix this. And then I'm going to go redo everything I just did. Now it's like a won't. Let's see if I might have messed it up. Well, it's fine. You guys had it written down, so. It's more complicated than it needs to be. Okay. So, hopefully, while I was fiddling around with that, we are going to type this into Desmos. So, let's go put that data in our calculator. Everybody go type it in. Make sure that you can do what we're going to do here because we're going to do a couple new things. So 0, 1, 2, 3, 4. And then, actually, I'm going to put it on this. Okay, and then we want the linear regression, so that's already programmed in for us. Now they did ask for it to be a plus bt. This gives y equals mx plus b. I don't think they will count off for this, but you could do s of t equals, put your y-intercept first here to be in that form that they're asking for. So the 6,826 plus the 864. Actually, it would be minus 864t. All right. So if we are using the model to predict the amount of salt remaining on day 3, when it says use the model, what is it telling us to do? Use the line. We're plugging it into the equation. We are finding S of 3. In fact, over on Desmos, I like to do this. I like to go call this, and then just do S of 3. Although you can plug it in whichever way you would like there. S of 3 is 4,234. So one of the biggest mistakes I see kids making is that right here they just use 4,250. They use the number from the table, but that is not the model. That's the data. Those are the actual values. The model is what the equation is giving you. So then I'm asked for the residual. So my residual is actual minus predicted. So for this particular data point, the actual is 4,250, and the predicted is 4,234. So if I subtract those two there, I'm going to get 16. A positive 16. Okay, so now it says, what does this mean in context of the problem? So when it says in context of the problem, you need to talk, like, you're talking about how much salt is in the salt shed, right? So you need to talk about the salt here. What I find a lot of times students do is they don't give enough context. Like, they tell me sort of what's going on. They'll be like, actual is 16 more than predicted. But you have not talked about Like that could be the truth for whatever we're talking about. It could be the money in your bank account. It could be lots of different population of a small town. It could be lots of different things, right? So we need to talk about the salt in the shed. I would say, because this already just goes actual minus predicted, I like to just talk about it actual minus predicted, although you can do the opposite. But I would say on day 3, you need to give a time period, because this is not true on day 1 or day 4 or day 7. On day 3, the actual amount of salt in the salt shed is going to be 16 tons. Here, this is a positive value, so that's telling me actual was higher than the predicted. So 16 tons more than the model predicted. For that. Now, we could do this for every single one of these, right? We could do it for 0 and 1 and 2 and 3 and 4. And we could see how far off each one of these are. And we could use that information to help us decide how good of a fit we have here. So, one of the things that we can do here is we can make what is called a residual plot. Okay? So, when you make a residual plot, it shows all the residuals for a set of data, and can be used to determine if your model is appropriate. If a model for a given data set is appropriate, the residual plot should appear without pattern. Okay, residual plot without pattern. Okay. If you can see a clear pattern in the residual plot, the model used was not appropriate. So whenever you're looking at a residual plot, the residual plot should look like this. It should be scattered and random. Okay? This is a pretty good residual plot because it is scattered and random. Bad residual plots look like a line or a quadratic, or have some sort of pattern that you see. We can do a residual plot on Desmos. If you look at the data that we plugged in, here it says residuals, E sub 1, and then there's a little button right here that says plot. And if you click it, it is going to put some dots up there. All right? And the residual plot is usually going to be like down close to the x-axis. We're going to do one by hand here in a minute so that you know exactly what's going on there. But it plots those residuals, and if you want to zoom into just the residual plot, you can click this, and we can see, I don't know about that, it's really hard to tell with only 5 data points. You would really want to have more data points than we have here. But this goes down and then back up. We would need some more data points before we really decide whether we thought this was a good fit. Or we could use some different types of regressions. So like for example, if I switch this to an exponential, my residual plot might actually look a little better. It's a little more scattered there, even though, let's go back to linear. Another thing to consider is how close your dots are to the x-axis. Because the closer your residuals are to 0, then the closer your line is to fitting, right? So linear, I don't know, I think exponential might actually be a little bit better. Your points are a little bit closer. They're a little bit more scattered around there. So it's a good thing to look at here in this case.
Question.
Yes.
People
that'd be perfect. Yeah, so if every single dot is right there on the x-axis, then you have a perfect fit. So, like, let's look at an example of that. If we had, like, let's just do one we know is going to fit perfectly. Like, if I have 0, 1, 2, 3, 4, and I do, like, 100, 80, 60, 40, 20, right? This is a perfect line. So if I do my linear regression, I get an r-squared value of 1. That's a good sign. But if you do your residual plot for that one, just everything's right on the line. So if you get a residual plot that looks like that, then your fit was perfect for that. Good question. All right, so back over here to the notes. For example 2, an exponential regression was used to model a data set. The residual plot for the exponential regression model is shown, that should say to the right. I reworked these to try to use less paper here. Which of the following is the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot? I've kind of already given this away. We've got not appropriate or appropriate. So exponential model is not appropriate because the residuals show no pattern. That's going to be false every time, because if a residual plot shows no pattern, that's a good thing. That means the plot does work well. So that would be false no matter what this graph right here looks like. The exponential model is not appropriate because the residuals show a pattern. Now that could be correct, but do you guys see a pattern over here on your residual plot? It looks pretty scattered and random, right? So that's not going to be our answer. C, the exponential model is appropriate because the residuals show no pattern. Here's what we want right here, right? We don't want a pattern with our residuals. Now, on our actual graph, when we actually graph the data, we want there to be a pattern, right? We want it to look like a line or a quadratic or whatever. But the residuals are telling you how far off you are, and you want that to be scattered about. And then D says the exponential model is appropriate because the residuals show a pattern. That's going to be false every time, because if you have a pattern in your residuals, that's a bad thing, which means the model is not appropriate. Okay, so a group of AP Pre-Calculus students, in example 3, used a set of data to create linear, quadratic, and exponential regression models. After creating the 3 models, the students created a residual plot for each model type. See above. Based on the 3 residual plots above, which model was most appropriate for the data? Give a reason for your answer based on the residual plots above. Okay, so here is the residual plot for the linear regression. Here is the residual plot for the quadratic regression. And here is the residual plot for the exponential regression. Which one is going to be the best choice for this? That exponential right there. Because linear and quadratic both show a pattern. Another thing to look at is look over here at your your y-axis. These residuals right here are a lot bigger than these residuals right here, right? The exponential regression is only off by like 0.1-ish for most of these, whereas the quadratic regression is off by like 2 or 3 or 4 on most of these. This one is off by 15 up here, right? So we would say something like the exponential model is most appropriate because the residual plot shows no pattern. And it helps, I'm going to put, and the residuals are relatively small. Now, the pattern is the biggest thing. If you see a pattern, that tells you you've got a bad model. But the size of the residuals is sort of like another thing to consider. Okay, so I made this problem yesterday because I think it is helpful, although I do not know whether or not you guys will have to create a residual plot by hand. If you do, the numbers will be very small there. But I think it's really helpful to create a residual plot by hand so you know what's going on here. So I created this example for us. I was inspired by the fact that Lauren Edwards says he's going to maybe play tennis. So if he does, I am predicting his performance here. He's going to stay late after every practice, and he's going to practice 50 serves on his own. And each day he's practicing the number, he's marking down how many serves out of those 50 that he misses. All right. So on day 1, things are not going so well. He misses 29 of the 50 serves. But on day 2, a little better. 3, a little better. By day 6, he's down to just missing 7 of the 50 serves. Right. So first thing we're going to do is find a linear model. So we're going to do this first one together, and then I'll let you guys try the second one on your own. So we're going to pull up Desmos here, and we're going to put this data in. So we've got, let's just get rid of that one. We've got 1, 6, we've got 29, 22, 15, 12. So what else? 8, 7. And we want to do a linear regression. So the first part of the question just asks you to find that linear model. So S of D would equal negative 4.42857. I'm going to use a D instead of an X because that's the notation that they're using here, plus 31. So if we are doing this by hand, I want to think about the actual minus the predicted for each one of these, right? So I'm going to do this to make it a little bit quicker. I'm going to copy this. I'm going to say S of, I'm going to use an X instead of a D just because Desmos sometimes does not love it if I use, it'll probably work with a D, but I'm not sure. There. And so if I do S of 1, my prediction is 26.57143. So the line predicts that he would miss 27.6-ish serves that first day. So if I want the residual, I'm just going to do 32 minus that number. And I will get 5.42857. So if I'm making a residual plot here, then over here on this graph, this is days, and then on the y-axis I have residual. So for day 1, I would have 5.42857. So day 1 is 5.42, somewhere about right here. And that's showing me that my actual is a little too high, right? My actual is higher than the graph predicted. So then I would go to the next one. I would do S of 2. And then S of 2 is 22.14286. Alright, and then I just have to take my actual minus the predicted. That one's going to be small. I'll just get 0.14286. No, negative 0.14286. And so on day 2, this is going to use a different color for my dots. Here's my first dot. Here's my second dot. It's going to be almost on the x-axis. Okay, here that makes sense. S of 3 is 17.71429. And if I do 15 minus that number, my residual is going to be negative 2.71429. So that on day 3 would look about like this. Keep on, honey. Day 4, I got 13.28572. And if I subtract those, I've got negative 2.28572. And so I can graph that point at 4, negative 2.28, will be about right here. Got 2 more, got S of 5. That's going to give me 8.85715. If I do 8 minus that, I'll get negative 0.85715. So that point would be about right here. And then for our last one, we would plug in day 6, and we get 4.42857. And if we do 7 minus that, we're going to get 2.57142. And that will be about right here. Okay, does that make sense of what we're doing there? We're just find the predicted, do an actual minus predicted for each value, and then we're plotting that. So we can see these 2 points, the prediction was lower than the actual. Here, the prediction was higher than the actual because we got a negative there, or the actual was lower than the predicted, we could say. For that, do you think it looks great? I mean, it's only 6 data points, which makes it a little tough, right? So I don't love it. It does kind of look like a little bit of a pattern, right? Now that could be just due to variation, and it's as good as we're going to get. But I want you guys to try the same thing for the exponential model. So your data is already in. All you have to do is change this to the exponential model. You're going to write that down here. And then you are going to calculate the predicted and subtract for the residual for all of these. Okay? So try that for everything that you have here. See what your residual plot looks like for the exponential. Okay? think I changed that one. That's the one. We've done it. I did it with these numbers. So either way. Yeah, that's the way. Megan has pointed out that the table that I have in the middle of the column for this one, like up there at the top, is not the same as the tables that I've got over there on the side. I was using the table down. Oh, did I even? What did I type in though? I might have like a whole disaster here because of this. I typed in the top table and then I used the side table for my residuals. Oh gosh, it's too much work to go back and redo it too. We're going to pretend we didn't do that because it's going to be too much work to go back and redo it. For that, my line's bad because I used the original data, but then I was using these numbers over here on the side, which is not good. But pretend we didn't do it. We should the numbers should have matched in both places. I changed the problem. I think the ones up here, I think this 29, I think that's what I wanted to use. But then I didn't change it over here in this table also. So I'm not going to have us go back and redo this whole thing because it will take too long. It's already kind of a lengthy process. There's a reason there's a button there. We're not going to do this by hand often. Let's, I'll fix it for third period, but it's too late for you guys. I have used the wrong numbers right here. We really should have been using 29, 22, 15, 12, 8, 7. So some of these are correct, but some of them are not, because really it's just this one though. It's just this one. That should be a 12, and this should be a 29. I could actually, it's not that bad to fix it. So if we do, for the exponential 29 here, this stuff, the predicted does not change because if you were using the correct data like I did, I used what I meant to be the correct data right here. So the residual, the predicted does not change, but the residual changes quite a bit right here. That is going to be 0.408. And then for number 12, day 4 where we have 12, we should get 0.2399. So let me fix these dots over here. 3, 4. So this one is actually only 0.48, and this one is right here. If I fix this one up here, I'll get negative 1.28572 here, and I will get 29. So this dot is really right here, and the fourth dot is 0.28. Right there. Doesn't change too awful much about what that looks like for our linear. We still have possibly a pattern, right? It does help out our exponential. How's our exponential regression looking now? Or residual plot looking now? We're pretty close to the x-axis, and we're pretty scattered, right? There's not a big pattern right here. So now that I've fixed my horrible mistakes, I would say exponential because the residual plot does not have a pattern. Okay, sorry about my mistakes there.